All right, we are going to continue with polar coordinates today, our second day on polar coordinates. And we're going to start by talking about how you can change an equation from one form to the other, which will be pretty similar to what we did in terms of changing a specific point, coordinates from one to the other or back and forth. And then we're going to talk about kind of some general basic polar graphs and their equations associated with the graphs. So let's go ahead and get started. So when we're converting equations between coordinate systems, we can actually just, like I was mentioning before, we can just use the same formulas that we use to convert specific coordinate points to convert equations. So if you recall, those formulas that we used, x equals r cosine theta, y equals r sine theta. We used theta equals tan inverse of y over x. We used r squared equals x squared plus y squared. We can use all of those here, depending on which direction we're converting from rectangular coordinates to polar coordinates or polar coordinates to rectangular coordinates. Okay, so this first example, you're converting 2x minus 5x cubed equals 1 plus xy into polar coordinates. Now note that we're not actually graphing these, at least not at this point. So right now we just want to write it so that instead of x and y, this equation is in terms of r and theta. So if you think about it, what we need to do is we need to get rid of all the x's and all the y's. So if we replace them using the formulas we used last time, replace the x with r cosine theta, replace the y with r sine theta, then look what we have here. We have 2r cosine theta minus 5r cosine theta, the whole thing cubed, equals 1 plus r cosine theta, r sine theta. Okay, so we'll just try to combine some terms and simplify it as much as we can. So 2r cosine theta minus 5r cubed cosine theta cubed, 1 plus r squared cosine theta sine theta. Now note that everything there, I know it looks a little bit like as if we might distribute, but remember these are all just one term. I've just written as r times cosine theta, but it's really just r cosine theta, r sine theta. So you can group those together. R times r is r squared. And that's it. Again, we're just trying to convert from one form into the other in terms of the equations. We're not trying to make it any more complicated. We're not graphing them at this point. Not these complicated ones anyway. So we just want to get the equation in terms of x and y all into r's and thetas. Let's go ahead and look at example 2. You are converting r equals negative 8 cosine of theta. Okay, so if you're trying to think about, okay, how do we replace this? There are a couple of ways of going about this. If you see cosine theta by itself and there's no r next to it, normally if it were like, if you saw like r cosine theta, you would say, oh, we can just replace that with x. That would make it really easy. And so what we can do to make it that easy for ourselves is if we multiply the right-hand side by r, we can multiply the left-hand side by r. So we can work with r squared equals negative 8r cosine theta. And this allows us to also not have to deal with the square root on the left, right? On the left, if we were to replace r, it would have been the square root of x squared plus y squared. But now that we have r squared, we don't have to worry about a square root. We can just replace that with x squared plus y squared. Right, so this left-hand side is x squared plus y squared, and on the right-hand side, remember we were trying to make it so that we had r cosine theta nicely lined up there. We can replace that with x. So on the right-hand side, we have negative 8x. And again, we're just trying to write the equation, instead of being in terms of r and theta, write it in terms of x and y, which we were able to do successfully. Okay, there are a few basic polar graphs that we are going to go over. In particular, we're going to go over lines, equations of lines in terms of polar coordinates, and then we're also going to go over circles. As we go through lines, you're going to probably start thinking, this is a lot easier in rectangular coordinates. I know you're used to that, which is fine. Polar coordinates aren't, polar graphs, polar coordinates, polar equations aren't really necessarily useful for those simpler things, but for more complicated things, for things that are not functions, it's actually easier, as we will see with circles. It's actually a much simpler equation that we'll end up working with when we're working with a polar equation rather than a rectangular Cartesian equation. Okay, so let's start off with some basic lines. So the first one here is r cosine theta equals a. Now, if you're trying to think about what kind of a line do we have here, you can think about converting this into rectangular coordinates. R cosine theta is equal to x, so this would really just be x equals a. A is some constant, just a number. So if we have x equals a number, you'll recall that really is just a vertical line, right? So if you have r cosine theta equals a, that is just going to be a vertical line. All right, the second one, well, if we're thinking we have a vertical line, if we're trying to come up with a horizontal line, we would want y equals a number. To get y, we would have r sine theta equals a number. Right, so that's the second one. So r sine theta is equal to a. Again, think about it, converting that equation into rectangular coordinates, and that would be y equals a, and that would be what you naturally think of at this point as a horizontal line. Okay, the last one, well, we have a vertical line, we have a horizontal line, what about everything else? So the last one is simply theta equals, and we use this other Greek letter, I don't know if you've seen it before, it's beta, B-E-T-A. So it's really here to just represent a constant, but it means that it's going to be an angular measure, just so that you know it's not what it represents. Okay, so what is this? Let's think about this in terms of rectangular coordinates. So if we were to convert this into rectangular coordinates, last time we said if you have theta and you're trying to convert into rectangular coordinates, you would change that to tan inverse of y over x. So we'll write that in. So tan inverse of y over x is equal to beta. Now let's say we didn't want to write this with inverse tan. We wanted to write it with just tangent. Kind of simplifies it for us a little bit. So if we did that, that would be tangent of beta is equal to y over x. Okay, so that's still a little bit hard to really see what kind of a line that is, but normally when we do work with rectangular coordinates and we're trying to graph a line, you try to get y by itself, right? So let's do that here. So we'll multiply both sides by x. So we have y equals tangent of beta times x. Now I've kind of put tangent of beta in parentheses there. Hopefully that makes it a little bit easier to see. But now you might notice, okay, this looks like y equals mx plus b without the b, which is exactly it, which means that tangent of b is your slope. Okay, now there is no plus b, so that means that this must be a line that goes through the origin, or goes through the pole, and it has a slope of tangent beta. Okay, so we're so used to thinking about lines in terms of the y-intercept, in terms of this m, the slope. And now instead of that, we're thinking of it as theta equals beta, which means whatever that angle measure is, that's how much it's going to, the angle at which the slope is. We're so used to thinking of slope in rectangular coordinates as tangent y over tangent x. Well, if you look at this, remember that tangent is really just y over x, so that does in fact give you the slope. All right, let's take a look at some examples. So I'm doing this in different colors so you can easily tell, so if you want to take notes in different colors, feel free to do that. So the first one we have here is r cosine theta equals 4. Okay, so we remember that r cosine theta equals 4 is going to be a vertical line. So this is a vertical line going through 4. Okay, so we find 4 on the x-axis, right? R cosine theta is x equals 4, so x-axis, a vertical line going through 4. All right, the second one, r sine theta is equal to -3. So again, r sine theta is equal to y, so this is a horizontal line going through -3 on the y-axis. So on the y-axis, find -3 and draw a horizontal line going through it. Okay, here's the tricky one. Theta equals 3 pi over 4. Okay, now think back to number 3, or look back at number 3 when we talked about basic polar graphs. If you have theta equals some angle measure, in this case, the angle measure is 3 pi over 4. So you can think of it this way. Think of it as, we know it's a line that's going to go through the origin. We just need to know what the slope of that line is. So the slope of that line is tangent of 3 pi over 4. What's tangent of 3 pi over 4? All right, think back to your trig. 3 pi over 4. Reference angle is pi over 4, which means the value is 1. 3 pi over 4 is in quadrant 2. That means tangent is negative, so the slope is -1. So you are going to draw a line going through the origin with a slope of -1. So theta equals 3 pi over 4 is going to look just like that. All right, we have one more set of basic polar graphs to go over, and these are circles. So with lines, not terrible, but probably still easier to use rectangular coordinates to talk about lines. Well, I personally think it's pretty cool to see how it relates, and thinking about slope as an angle measure, and how it relates to tangent, change in y over change in x. But in terms of the equations of lines are actually not too bad in rectangular coordinates. But if you remember circles, if you think back to Algebra 2, when you were learning about circles, do you remember those equations? Those are fairly complicated equations, right? It was some form of x squared plus y squared equals r squared. But then what happens in the denominator will change how the entire circle is shifted, or where the center of the circle is. So there are a lot of things to account for when you're working with circles. Dividing everything through, so you have x squared and y squared by itself. You might have x minus something, y minus something. So this is an example of where polar graphs can kind of make it simpler to explain. Also, the reason why it's kind of more difficult to, with equations of circles, you think about it, circles are not functions, right? So once you get into that realm, if you're even trying to graph that on your graphing calculator, if you were to graph that, you'd have to split it up, right? Normally in rectangular coordinates, you have y equals. If you were trying to get that x squared plus y squared equals r squared, and get that y by itself, you're going to end up with that plus or minus square root, and you'll have to enter it in as positive square root and negative square root, and it gets messy. So with polar graphs, you actually have a function on your graphing calculator. We won't get there yet, but you are able to just put in one equation in polar form, and that will give you the graph of a circle. Okay, so the simplest graph for a circle is simply a circle that is centered at the origin, at the pole, and it has a radius of some value. So that equation is this, r equals a. Again, if it's helpful to kind of relate it back to rectangular coordinates, we can go ahead and try to relate this back. So r is equal to square root of x squared plus y squared. And if you square both sides, you end up with that x squared plus y squared equals a squared. Normally that a value, if you remember it in Algebra 2, you would have to be that a value would have to be your radius. And if you relate that back to the equation that we have here, it's just r equals a, and this is a circle centered at the origin with a radius of a. All right, we have 3 other basic polar graphs of circles. So we're going to go over 2 and 3, and then number 4 is really just a combination of 2 and 3. Okay, so number 2, we have a, let's say you take that circle, the very basic circle that's centered at the origin, but say we wanted it to be centered somewhere along the x-axis. So with some center a comma 0. Okay, well in that case, this is the equation, r equals 2a cosine theta. Now we could absolutely go into putting this into rectangular form. You'd probably want to multiply both sides by r, replace the r squared on the left with x squared plus y squared, replace the r cosine theta on the right with x, and then you'd end up trying to get it into the right form with a couple of changes in there so that you can very easily see where the center is. Now obviously that incorporates a lot more. You can hopefully see that r equals 2a cosine theta is a much simpler equation that we can use. So this is a circle centered at a 0 with the radius of the absolute value of a. Okay, so the only thing to really note is you will see, like for example, r equals 20 cosine theta. It's kind of natural to just say, oh, the number in front is going to be what the radius is, but note that it's 2 times a, right? Not just the number in front. That gives you the radius. All right, similarly, if we had a circle and we wanted to center it along the y-axis, that would be r equals 2 times b sine theta. This is a circle that's centered at 0 comma b with a radius of the absolute value of b. Okay, so those are kind of the simpler equations. If you have a circle specifically centered on the x-axis, a circle specifically centered on the y-axis. But it could be anything, anywhere, right? It could be centered anywhere on your graph. So this last one is going to be combining both 2 and 3. So combining where the x-coordinate is at a, the y-coordinate at b. And here is the equation, r equals 2a cosine theta plus 2b sine theta. This is a circle that is centered at a comma b. And then the only tricky part here is, what is the radius? The radius is going to be the square root of a squared plus b squared. Okay, it's a circle centered at a comma b with radius square root of a squared plus b squared. All right, let's go ahead and do some examples. Okay, so again, remember, it's always 2 times a or 2 times b in order to get your a and your b value. So don't just take that 4 or take that 7 and run with that. It's always half of that, right? Okay, so r equals 4 cosine theta. So you see the cosine theta, you should automatically think, okay, this is a circle that is centered on the x-axis. Okay, so half of 4 is 2. So you can think of rewriting this if you'd like, but r equals 4 cosine theta is 2 times 2 cosine theta. All right, so this is going to be centered, a circle centered at 2 comma 0. Okay, there's 2, 0. And it has a radius of a, which in this case is 2. So we just count out 2 in all the directions we can and draw our circle of radius 2. All right. Next we have r equals -7 sine of theta. Now again, if you need to rewrite it, feel free to. Think of this as 2 times -3.5. Okay, so it's always 2 times A or 2 times B, depending on if it's cosine or sine, or if you have both combined. So this would be at negative 3.5. Okay, so it's centered at 0, negative 3.5. And then this has a radius of 3.5. All right, so that means it's going to extend all the way out to 0 up at the top, all the way down to 7 at the bottom, and then just extend it out 3.5 to the left and to the right, and draw the best circle that you can. All right, last one's the easy one, right? R equals 7. If you have just R equals a number, that is simply a circle centered at the origin with a radius of 7. So centered at the origin here, radius of 7. So we'll go out in all directions out to 7. And there is your circle. So you can kind of see how that equation, R equals 7, is so much simpler than x squared plus y squared equals 7 squared, right? So it's not always the case that polar coordinates are necessarily will necessarily make equations easier to work with, but in particular when it comes to things that are not functions, like circles, for example, using polar coordinates do actually make it a lot easier to deal with. You'll see it in calculus that if you are working in polar coordinates, it's actually probably a lot easier to do things with than if you have a more complicated equation in terms of x and in terms of y. Instead of working with x squared plus y squared equals 7 squared, if you just work with r equals 7, it's probably a lot easier to be able to do things like find derivatives, which you'll get to when you get there. But this is really just a sneak peek into how you can be using polar coordinates. What are they used for? How does it make it simpler in some cases for us to use for higher math?